around is
Fair game.
So here's a question I have for you. I don't think I put dielectrics on the last test, did I?
Yeah, you did.
I did? Okay.
Yeah.
Then no dielectrics on this test.
Cool.
Yes, it is. Magnetic materials are much more complicated, actually.
Will there be dielectric energy? In what way would that be complicated?
No,
Alright, good. So nothing chapter 5.
I don't know what's in chapter 5.
Capacitors and dielectrics, which were actually on the last test.
I have the last test right here if you want to check that.
I remember it being on the last test.
Okay. So after the exam, we talked about the energy in fields.
Right.
Yeah.
All right. Energy in electric fields and dielectrics, no, not that, there's no need for me not to have it on this test, but I'm not going to go out of my way to put it on the test. And on the test that I've written so far, it's not. So, what did you say?
No chapter 5.
Energy and dielectrics. Okay. I have no idea what that is. That must go here. That's all the homeworks. I did not do what I told you I would do, and Josh is calling me on it, which is to give you the list of fair game topics.
I just found out you started making the exam at 11 this morning, so it makes sense that you didn't upload it last night.
That's correct. I intended to, but then
It's okay.
the physics 2 exam needed to be.
I know.
No, I don't know what I was doing.
It doesn't matter. You're
I
over
can't actually remember what I was doing, but I was doing something.
It's fine. It's
And
okay.
Took all of my attention.
It's not.
Okay, so definitely, and Adam, I think, asked for me to talk a little bit more about Lorentz transformations and 4 vectors and those sorts of problems.
Well, we also need to know, boosts would be very appreciated, but what about the energy momentum tensor?
We never covered
Not
it.
at all.
Okay.
No energy momentum.
No, and I haven't lectured on it at all, but you could, reading the chapter, think, uh-oh, he's going to put the Maxwell stress tensor on this exam. The answer is no. No Maxwell stress tensor. Stress, yes. Tensor, no.
Different kind of stress.
Not only your dielectrics with permeabilities given by
Don't forget ferromethodology.
That was fun, I must say.
Any complex variants?
And I gave it to Professor Key, and he started working on it.
Did you get the part where you were looking for virtual current?
Yeah, he stopped when he looked at me with the virtual current, like, do you know what you're talking about? But he didn't question me, because I have to vote on his tenure case yet.
Ah.
And then did he get to the end?
Actually, I've already voted on his tenure case, and he knows it, so. But he still was very polite. What? Oh, okay. Yes. When did that happen? Well, you know, Professor Dwyer is probably taking a long. Are you filming me?
Yes.
A long lunch because he's going to be working late.
All right.
So, what do you need? Nitrogen? Yes. In my office. Pink key. I always keep a bottle of liquid nitrogen in my office.
Doesn't have film.
Okay.
Still, what about Ohm's law and magnetic susceptibility?
Ohm's law.
Still no Ohm's
No.
law. Okay.
Okay.
Susceptibility was on the left.
Have I talked about
I don't know that.
the pointing vector yet?
Barely. You.
Yes.
Just, yeah, okay. I introduced the, let's call it the DC pointing vector. Not DC, well, the steady state pointing vector. Soon we will have a traveling wave pointing vector, which is the same thing. And the retarded pointing vector, which is just not as smart.
So I'm like, is that the actual name of it? That's
Later.
kind of a little insensitive.
So not for this.
No pointing vector.
But the concept of the pointing vector and applying it as E cross H would be fine. Your question was about or someone was saying, asking about, why don't I start at class 10 and sort of work my way through? So on my list of topics for class 10, I had the space-time interval, Lorentz transformation, length contraction, time dilation, four current, and four vectors and tensors.
So,
And all that is fine.
we never actually used, but.
Yeah, but I could ask you, for example, to transform it. What does it, you have a four vector, what does it look like in another frame, another inertial frame? Okay, so for a quiz, I already asked you to transform a tensor, a field tensor. I could ask you for the exam to also transform a four vector. So do review how to transform four vectors. Okay? Yeah. You won't worry about, no, I'll just continue. Next class, 11, I discussed vector calculus in space-time, which really was just how do you write out in the component form with four vectors and tensors. Well, we didn't do a whole lot with it other than for me to show you. Is there anything in there?
Yeah.
Good. I mean, my whole office is full of nitrogen, but we want it liquid.
Probably more nitrogen in here than.
In the office, yeah. One of the things you have to watch out for, by the way, for those of you in SPS who play with liquid nitrogen all the time, is that if you empty one of those bottles into a room, you may end up pushing all the oxygen out of the room, and then you will faint.
That's bad.
And die.
Really bad.
No, it won't be bad. You won't know.
Well, for just people who shitty, well,
Yeah.
that would be a problem.
Mind you, actually, if you think about it, you know, as far as finding a body, it's the least worst case.
Well, no, the problem is if you see a body and then you walk into the nitrogen and then you die.
You have to open the door to get in.
Right.
But if you open the door and get in, wouldn't it equilibriumize?
Back to
Back to that.
class 11, I had listed as the four vector potential, the field tensor, deriving the relationships between the field from the field tensor and the boost tensor. And then I have written here Maxwell's equation. I have no idea what I meant by that. But I must have talked about Maxwell's
The
equation.
nitrogen equation with the four current and the four.
Yeah, probably the four vector,
You
the
just,
four space Maxwell equation. But look, you can write it in a compact form. I'll come back and maybe talk about
Okay.
this. But
Just when they were deriving Maxwell's equations using just the field tensor,
yeah,
in Ohanian they do everything except, I believe it was Ampere's law. And I was just wondering if you could quickly show how to write that. Because
oh,
Faraday's law, they
I'm not going to do it in front of you
Okay.
now. I'd have to prepare.
Okay.
Right, so.
They did.
They either did Faraday's or Ampere's. They left the other one.
There is a,
No, they did Faraday
okay,
later.
so deducing Maxwell's equations from the properties of or deducing the properties of the field tensor from the rules of Maxwell's equations is not trivial and involves the selection of let's say the rules that you're going to apply
Right.
to the four vector potential.
Right.
And so, you know, for each way that you derive things, you know, you might use what's called a Lorentz gauge.
Yeah.
So you select the rules that apply.
Right.
And then you ask what's the outcome of that set of rules.
Okay.
And okay, you don't completely select the rules. You know that certain outcomes have to apply.
Okay.
And then you say, well, this outcome could happen if the field tensor is symmetric,
Okay.
anti-symmetric.
Oh, actually,
This could happen if that. You say, okay, if that, then what are the consequences?
Okay. I think I might understand here. For
And so it's more complicated than, I have selected a path
Yeah.
through the logic
Okay.
that leads to where I want to be and to a simple, straightforward conclusion.
Right.
if there's time at the end of the course, I'm going to talk about other paths through the logic.
Okay.
But I would have to review for myself what path I chose.
Okay, very well, yeah.
Okay. Then we went to magnetostatics and Biot-Savart, Ampere's law, and the vector potential.
So all the topics you have just listed from class 11 are fair game.
Yes. I addressed the fact that you can solve some problems using a magnetic scalar potential. And then last class I told you I'm not going to test you on the magnetic scalar potential. But I think I was asked to go over a vector potential problem and go over doing something with vector potential, and I will. Okay. I have a note here with magnetic monopoles with a question mark. And actually, I did not discuss magnetic monopoles in this class. There's a nice section in Ohanian. You can read it if you wish, but I'm not going to do it.
So you're
No,
not going to test us on
no
that.
class.
So I'm not testing you on it. Oh,
The classic
Magnetic
physics 2
model.
question you always ask.
the question, how would these equations change if, or which of these equations would change if magnetic monopoles exist? That could be a multiple choice.
Okay.
It could be. It is right now,
When you say-
but I might take it out because I just confessed to having it in there.
Well, I mean, I already knew it was gonna be in there.
When you say-
Even in-
When you say exist, do you mean mathematically exist or exist but
Physically.
we haven't observed them yet?
Yeah, they don't exist at all. We haven't observed them yet.
How would physics change if they existed?
How would you rewrite
That's
Maxwell's
too big a
equation?
question.
It's
And that's actually a fairly complicated question that would take too much time. More to the point might be, which of these equations have to be changed? If, no.
No, he passed that to physics 2 all the
Choice.
time. That is literally a physics 2 question.
But you can think about how. It's good. That way you'll be prepared for when the monopoles are really discovered. Okay.
Instead of in California.
Class 14 was B and H. That's all that I've written here. B and H. And I'm probably going to lose my voice in about 10 minutes, so.
We should quiet down so we can hear him better, so he doesn't have to talk as loud, so he doesn't lose his voice as quick.
That was what she said.
Okay. Class 15, time-varying fields, Faraday's law, the concept of inductance, the concept of displacement current. Yes. All there. On the test. If it isn't, it's an oversight on my part, which I will correct. So, then 16, I have listed conservation laws. And that's where I got the definite, that's not where I got, but that's when I defined the pointing vector.
16 was last class, right?
Yes. No. 17 was the last class, and in 17,
You never did.
We had a quiz and you said, okay, this may or may not be in the test.
yeah, right. So class 17, I didn't introduce new material.
Yeah, 16, you never finished that integral thing,
That integral thing.
where you had to add the scalar to a vector and never, it was never fixed.
You're right. All right, so those are the topics.
And those are online.
And
They will be.
I believe someone can check for me that I posted all of these lectures online. All of the-
Yeah.
All of the PowerPoint slides.
You comboed 9 with 10.
Yeah, 10 with 11. And then
There's another slide.
I took a quick look and it looks as though Eli has put up most or all, I'm not exactly positive, of the actual lecture presentations for each of those classes.
I believe the only one I left out was
The one I
13.
told you.
Yeah, the one you said, you are not going to put this up,
Yeah,
or
I
else.
totally screwed up. But
It was accidentally up for like half an hour before I realized, oh F, I wasn't supposed to have that up, and then
So I can expect that I'm gonna get a call now.
no, I took the videos.
There were no views?
I don't think so. I made them
Okay, good.
private and then I deleted them. So if anything is left, they
Okay.
are unviewable.
Class 16
So now I
topics.
will ask questions.
They're all
I answer
fair game.
questions. What?
Class 16 topics are fair game? All-
Yes.
all of it?
All of them. Let's say especially class 16.
Okay.
Whatever I did in class 16. Yes.
In terms of inductance, you wouldn't expect us to do anything beyond what you did in class, right?
That's correct. And actually calculating the inductance of a simple system is sort of unfortunate that there are really only a few systems that you can easily calculate the inductance of in a reasonable amount of time. What?
Elliptic integral.
Yes, although I suppose, yeah, I did as an example. Did I do inductance per unit length of a coaxial cable?
Yeah.
Yes. That's a fair game. I like that one. So yeah, that would be only, it would be limited to variations on examples that I gave you and homework problems.
Okay.
We did have a single question on inductance from homework.
Will
It
we
wasn't,
use
it wasn't calculating inductance, but it wasn't.
Oh, did you ever find any like good examples of inductance problems from the book that you thought would be representative?
I think I did them
Oh, you did.
in class.
Okay, cool.
It was probably, let's say, inductance of a toroid, that's one you could do. Inductance of a solenoid, and inductance of a coaxial cable. All three of those are actually worthwhile practical problems. And they touch on the key concepts.
Go to
I'm
you.
not telling you to memorize any one of these. I'm hoping maybe instead of a toroid, I'll make a Mobius toroid. So, because I said
Mobius.
I'll throw a twist into the problem.
On the other hand,
Mobius.
Like a Mobius strip.
You say Mobius, I say Mobius. Professor Schroeder probably says Mobius. Is there an umlaut in there? Yeah. I'm going to go with Mobius.
And then calculating the dipole moment obviously be a question.
Could be.
Anything could be a question.
I think the question that Josh asked me is, what's fair game? No. Everything's not fair game. There are unfair games that I could play. I don't want to play unfair games.
So,
I want to play fair games. I find that a sufficient number of you fail, even when I tell you what's going to be on the test.
so basically, if you didn't go over it in your lecture notes, or it wasn't assigned for homework, or it wasn't on a quiz, then if it's in the book, we shouldn't reasonably expect to see a calculation or conceptual problem about it. Maybe. That's it.
Say that again. So there's
Your lecture notes.
Okay, so let me talk a little bit about lecture.
Okay.
Okay, lecture involves a half-assed derivation of an idea. All right?
Okay.
Just so you get an idea where things come from.
That's too long.
And the occasional example. It's okay, I permit myself
All right.
to say half-assed on tape. It's not tape anymore. But I
Which is
don't
too bad.
really expect you to reproduce my half-assed derivation.
Do you expect us to reproduce any kind of derivation?
Well, in order to solve some problems, you have to understand what's going on
Right.
and make some logical steps. Okay. So, I don't know how you define the word derivation. I don't define it that way, right? If it requires 10 steps to solve, it's still not a derivation. It's just an application. So that's the way I'm going to define it. I'm going to say that there are no derivations on a test.
Okay.
I don't tend on tests to put show that given this axiom, this set of axioms, that this must be the consequence. Right? So back to the half-assed derivations, plausibility arguments, and then examples. If I do an example in the class, that's a definite possibility.
Okay.
Yeah, it's something that I thought was compact enough and meaningful enough to give as an example. And if I think it's that, then it's testable.
Okay.
Or something related to it is testable. You already had one test from me and 6 quizzes, so I think you have something of an idea of what sorts of things I will do. Let's say the random thing here for you, the unpredictable thing, is that you don't know what the multiple choices are going to be like. And the multiple choices do address, let's say it's like sometimes deeper conceptual question. Do you really understand how this works? And the understanding might have to be at the level of derivation. But usually, you've seen it before, or it's easily deduced. Easily for me. Yeah.
For magnetization,
Okay, I'm going to confine us, by the way, to linear magnetization, linear permeability. Let's say B is equal to mu H, and mu is a linear function of applied field.
Okay.
Right? No, mu is a constant. Sorry, that's what I meant. Mu is a constant. And magnetized materials, where I just state this material has a magnetization that may be complicated, but it's just there. All right? We won't be doing things with nonlinear tensor susceptibilities.
okay. I'm just wondering, like, for generating bound current and bound surface current,
Yeah.
I'm trying to get a deeper conceptual idea of that. Why is it the curl of the magnetization that's so important? And
What do you think of this way? That the vector. Okay, I don't know that this is going to help at all, but I'm just going to state it, which is that the magnetic field is the curl of the vector potential. All right, and the vector potential has a very simple relationship to the currents. This is sort of complicated in here. So R minus R prime.
right.
All right. dV prime. All right. So that's really, in some sense, simple.
Right.
And then the magnetic field is the curl of it.
Okay.
So the relationship between bound currents and magnetization
Mm-hmm.
is the curl
And just-
relationship.
and
Because
just-
that's the currents, bound or unbound.
Mm-hmm. So when there's something that has constant magnetization throughout the center of it,
Yeah.
it doesn't have any bound currents because the curl is obviously zero.
Yes.
Surface.
But
No,
there is a
yeah, it doesn't
surface-
have any bulk bound currents.
Bulk bound currents.
But as Brian correctly said,
So,
when you transition from one material to the next,
yeah.
there will, where you have magnetization and no magnetization, there must be
A surface.
a surface current.
So is that because if you think about it like individual atoms, they're bound
Yeah.
currents kind of cancel out on the inside, but on the outside?
But not at the edges.
Okay.
Right, and it's the same way with the magnetization changes when the currents don't cancel cancel.
Yeah.
There's a whole derivation in Ohanian, but basically when the currents don't cancel, you find that it is the curl magnetization that matters. I don't know how to derive that. I hope that's not a question. But
That makes sense, in that kind of sense, that it's
but think of every single atom as a little circular loop of current.
right. So
Even though that's totally imperfect. But they kind of act like that. And then with the magnet, everyone's the same. Like, and then.
Yeah, I think he's got it.
Yeah.
Yes.
He's got it.
Thank you.
You know, we have another tripod.
I know.
Too late now.
Yeah.
Okay.
I figured rather than delay this any further, I'd just hold it.
Would you be willing to go over the last quiz that we had? Specifically the part where we had to find the magnetization of whatever object we were given?
It was an,
Susceptibility.
From the either susceptibility or mu, which one?
I actually don't remember the question.
I can.
So I had an object, I thought I had an object with
No,
magnetization.
it was an object with
Wait,
mu,
what's six?
with
What's
mu
the turn down?
inside a
Professor,
solenoid.
do you want me? 'Cause I remember the question.
Okay.
Do it.
That's good.
So the question was, you were given, you have a material with mu magnetization, or not mu, mu
Permeability.
permeability, and
It was inside a
it was
solenoid.
inside your.
Aren't they supposed to?
This is terrible drawing. This is filling the whole thing. Pretend it fills the whole thing. And you were told that this object has this susceptibility, and then asked to find the H field and the B field everywhere.
We wanted to find the magnetization first.
Yes,
You knew that
you
it
want
had N
magnetization
turns
first. But
per
once you have the
X.
H field and B field everywhere, the magnetization is really easy. Okay, so I'm going to start with that. So the first thing is that the H is, at least I found it most easy to do using Ampere's law equals your,
There's a faster way to solve it.
this is the way I did it. There
Only
might
the
be a
free
faster
current.
way.
That's good.
Great,
Oh,
so
that's
it's only
fine.
the free current. That's good. Why? Because the only free current is in the wire. All right, and then there is two relations between H and B. And the first is that mu H. Okay, thank you. So the first is mu H equals B, and the second is that H is minus 4 pi m. Plugging this into here, you get that H times
1 minus mu.
1 minus mu.
Shh, I'm doing basic math. So it's 1 minus mu equals. Physics is fine. For me,
Minus.
addition,
I
however.
dropped the minus sign.
I did.
Yes.
Don't drop the
Alright, there's a minus sign here though. Alright, so we're gonna make this mu minus 1. I did it right on this, I think. We're gonna make this mu minus 1. Alright, so you have H from here, and that gives you the magnetization through that. Once you have the magnetization, you can either directly calculate the B field or find out the current and then use Ampere's law.
The only thing
Yeah.
that messed me up on that question was that after in order to get the first problem, you had to do the second problem first.
You did.
You had to find H
Oh,
first.
yeah.
You had to find
Yeah.
H
Yeah,
first.
you had to do
And
part
so I was
B
like-
in order to do A, and then I.
So you find H
Yeah.
first, then you use that to find the
H
magnetization.
is just formula.
Yeah.
It was just a solenoid.
It's just a solenoid.
Yes.
And mu times that.
So it's just the
Wait.
solenoid,
Oh,
and
oops.
because they were the only free. There's something there.
And then you just add a
Yeah.
mu.
Okay,
So-
so now you know H.
Yeah. And you know all the directions because the only.
And you needed to know this.
Yeah. And you know the
And then
direction.
given H and B, which you've now, as Brian said, I'm just summarizing. You find the magnetization. And then, given the magnetization, you can calculate the surface current due to the magnetization.
No, why is the bound current, or why is the volume bound current 0?
Because you get a magnetization.
Magnetization is constant,
Because the curl of the constant. Oh, okay.
right? And then at the surface, you've just got, I can never remember whether it's M cross N
With
or
a
N
C.
cross N.
The surface is M cross N times C.
There's a C. There's not plus or minus, just times C.